Hi, everyone. Uh, this is Water as a Resource, Practical Applications of GIS and Remote Sensing. I am Josiah Thomas. I am from Denver, Colorado, born and raised pretty much my entire life. Went to school there and all. You'll see that soon. I specialize in water infrastructure asset management, GIS and remote sensing for climate resiliency, technical assistance for water and wastewater systems, funding and policy strategies for sustainable water management. My headshot on the right. That's me.
That's what I'm going to go over my background. Um, Section two is the critical issues. I'm going to frame the problems and establish a baseline and an understanding of the water industry globally and nationally. So we're going to go over the problems that we're facing. And then section three is going to be the power of GIS, remote sensing. It is currently underutilized, but could revolutionize efficiency and automate decision making, aka the wave of the future. Hop on. And then finally, we're going to go over the Green Space Project, which is my most significant GIS and remote sensing water project. So I feel like I want to get my wiggles out. Does anyone raise your hand if you want to get your wiggles out? Are we all tired? Raise your hand if you're tired. Yeah. Well, let's wake up. Wiggle. Yeah. Just a little wiggle. So I went to the Colorado School of Mines. I studied geophysical engineering. I am not sure if and someone raised their hand if you know what geophysics is or familiar have heard of it before. Anyone? A couple people. Good. Well, it's a pretty niche industry, but it applies to general mapping of the subsurface and mineral exploration slash oil and gas. So I studied and applied skills in Python, C++, GIS in the Esri suite, SQL, which is the sequence. Oh man, I don't remember exactly what it is. Sorry. Data processing, seismology, mapping, and sampling. And during my time at Colorado School of Mines, I performed collaborative research, software development for seismic wave scattering, and I published a paper on that research as well. So on the right, you'll see I have a little bit of a diagram rolling that shows where my skills have come from, where they lead in the next step, and we'll see it expand on the next step as well. But after school, obviously, I graduated and went into my early career roles. I was a mechanical integration engineer where I focused on asset management, asset performance management software, and the petroleum processes, petroleum refinement processes. Skills that I developed were everyone's favorite, Excel. We all love Excel. We love tables, petroleum engineering, and data management. That then led me to processing technician at a gravity and magnetic geophysical data acquisition company. I processed the data. I gained the tools I used were regional spatial processing softwares that were proprietary to that company, GIS, and obviously Python as well. And the skills that I gained, which are really pertinent today, are large scale, if not regional, data processing and cross functional teamwork as well. Which we're all working across teams here. We're all dipping our toes in different industries, so it's a really important skill to have. On the right, I'm just going to explain. It's you see the connections. We go from geophysics, energy sector, and GIS and data science into the energy transition, geophysical data analysis, and oil and gas asset management. This leads me then to my what I call post-COVID adjustment, where I took some part-time jobs and had some reflection time, and it ultimately took me from the oil and gas slash exploration industry into water and GIS driven problem solving. So that's where we're at today. And water and sustainability leadership. I am the project and funding specialist, obviously, at Sierra Nue. I, uh, you know, the general deal with what we do at the association, but I train over 50 systems, I publish articles, and I generally improve operational efficiency with all the systems I work with. Um, then I also am working as a project lead on the Green Space project. I provide it's a technical assistance venture applying GIS, normalized difference vegetation index, and parcel level mapping to cost-effective planning. I know that's a lot of words, parcel level projects. We're all trying to follow here. So The skills that I've developed are machine learning, remote sensing, UAVs, aka drones, and data validation and leadership. The focus of this project is generally the focus of this presentation, which is to translate complex data into actionable insights and partnerships with local and federal entities. And it leads us on the right diagram from solutions to sustainability and water resources into what I consider all of our presents or all of our current situations where we have so many directions to choose, and eventually we'll wind up choosing our directions and further refining our path, just like we did in the rest of the diagram. So that's the little diagram there. Then leads us away from my background and why is water resource management important? Why is water a resource rather than a commodity necessarily? Water is the most critical resource, in my opinion, that we have as a resource on our planet. It supports communities, ecosystems, and industries. We all know that it's very important, and it all sustains our lives as well and our careers. It is essential for health, food security, and economic growth. And in this industry, change and innovation really will lead us into the future. And unfortunately, it is required for the developing technologies, and hopefully my presentation today will help you guys understand the power of remote sensing still. So we go over aging infrastructure, funding complications, and weather extremes threaten the stability of many water systems. And data-driven management improves long-term reliability and resilience in the end. On the right, this is the drought monitor from August 26th of 2025. At the time, 27.7% of the nation was in drought, between moderate drought and exceptional drought. But obviously, it's variable. It changes all throughout the year. This is just kind of showing what it looked like a couple weeks ago, and we'll dive into it more later. So, the critical issues in water, we're diving into them. Aging water and wastewater systems. Many pipelines and treatment processes exceed 50 to 100 years of expected life service. Leaks, contamination, and structural failures increase with age, naturally leading to crises. The one crisis that I chose to example here was the Baltimore water crisis of 2022, where decaying pipes led to E. coli contamination in the drink water. Of course, I'm not an expert in that specific crisis, but it's just yet another example of we need to be replacing and being innovative in terms of our implementation of new technology. This leads us then to lack of preventative maintenance, which goes hand in hand with aging water and wastewater systems. Deferred upgrades lead to catastrophic failures instead of gradual improvements. I think that we're all very well aware of that. We need to be continually implementing new technology. The example is Jackson, Mississippi water crisis of 2022. Decades of neglect resulted in total water system collapse, leaving thousands without reliable service. Very scary. More critical issues, extreme weather exposure. Infrastructure isn't necessarily always built or updated for potential conditions and can break down when severe weather hits. Texas, the Texas winter storm of 2021, power grid and water system failure due to poor insulation and lack of preparedness. Yet another example of high costs of ignoring common sense upgrades. This is another big part. A lot of the times, certain um, individuals improperly implement and cost cut, cutting corners, ignoring established standards, and often creating bigger problems at the end of the day. The example is we're all familiar with the Flint water crisis, if not the most familiar with that crisis specifically. Skipping proper corrosion control to save money caused a public health disaster and much higher costs down the line. The final critical issues slide. Funding challenges. I'm curious, who would classify this as top five issues in water funding? Anyone? Yeah. What about top three? Top issue. Yeah. I think funding is unfortunately the largest issue we're dealing with today. Finding where we're dealing with finding the avenues to support our investment. Many water utilities also rely on outdated pricing models, leading to financial instability and improper rate setting. And finally, federal and state grants exist but are highly competitive, leaving small utilities at a disadvantage. Deferred maintenance creates a cycle of crisis response, increasing long-term costs. This also leads us to another top 5 issue, in my opinion, which is workforce retention and labor shortages. It goes hand in hand with funding, obviously, because you have to pay your people to make them work. Uh, there is, unfortunately, many experienced water operators nearing retirement with few replacements in the pipeline. There are also high turnover rates in rural and underfunded water systems due to low wages and high job demand. Training programs and pathways for careers are limited. They do exist, but some communities are left without the next generation of skilled worker. And finally, a 2022 AWWA report found that over 50% of water utilities are struggling to fill key positions, threatening long-term operation stability as well. Now, to break up the monotony and break up the doom and gloom necessarily, I'm going to talk about remote sensing for a second here. Tidal patterns. In the bottom left, you'll see we have variable tidal patterns that have been compiled using the above resources. Satellite altimetry, it measures sea level variation. Synthetic aperture radar maps tidal flooding extent even on sunny days or in the weather. And then finally, optical remote sensing tracks coastline retreat and saltwater intrusion. Additionally, we have drought and flooding, the GRACE satellites, gravity recovery and climate experiment, detect groundwater storage decline, general groundwater storage change, if it's increasing or decreasing, it's not necessarily just decline. The normalized difference vegetation index monitors agricultural stress from water shortages by identifying vegetation health. Thermal infrared energy measures surface water temperature and evaporation rates. Very useful in the water industry. We'll get into that later. And finally, microwave radiometry tracks soil moisture conditions across the basin. This is just an example. I'm not sure. This is the color bar at the bottom here. It shows that the water storage trend for millimeters of water loss per year is between -12 and 0 for most of the color bar. As you can see, the lighter image is from 2002 to 2014, and it indicates that we had significantly more water and significantly less water being extracted from the groundwater system in the Colorado Basin between those 2 decades. So as you can see, the difference is pretty dramatic. You have a lot of black, a lot of red, and then on the converse, you have still a lot of yellow and still a lot of red, but it's obviously a little bit exacerbated. So I just wanted to provide that as a specific example. We get into the power of GIS remote sensing, what everyone here has been waiting for. It revolutionizes infrastructure and resource monitoring by keeping water systems resilient under stress. It connects real-time and historical data, helping utilities track change over time. It enables predictive analytics and smarter decision-making processes, supporting proactive planning and not just crisis response. GIS and remote sensing provide for smarter, more resilient water systems. It's an equation, so it's math. It just maths out. Now, I figure everyone, I'm curious, it's on the screen, but who is familiar and would be able to reference it off the top of their head what GIS stands for? Raise your hand. Good. That's what I like to see. So geographic information systems, we are dealing with it in a lot of the aspects of our jobs now. What it is, and I'm going to break it into simple topic or conversation or simple explanation so that it's easier to understand my approach to it. It is methods for capturing, managing, analyzing, and visualizing location-based data. Location-based data being the biggest part of it. What it does, it combines software, hardware, and data to reveal spatial patterns, relationships, and trends. Why it matters. It is essential for managing water resources and making data-driven decisions. On the right, you'll see that is one of the most clear visualizations of what GIS is overall. You're combining layers, you're combining information, you're bringing it all together for an individual picture, which is the real world. Is anyone familiar with rasters versus vectors? Raise your hand. Are we familiar? Yeah. It's the two data types of GIS data, and it also applies to remote sensing as well. So rasters are grid-based data representing continuous surfaces. You have cells, aka pixels, each with a value. The raster representation is here on the right, obviously. Each grid point has a value, whether or not it could be zero, it could be a nan, which is a non-value, or a value. So examples include elevation models, digital elevation models, land cover and vegetation, precipitation, and temperature maps. Now this brings us to vectors. They are coordinate-based data representing discrete features. Discrete not meaning secret, discrete meaning individualized and isolated. They are made up of points, lines, and polygons. You see in the top right, it shows you points are single locations. That's pretty self-explanatory. Lines are linear features, and polygons are areas. It's exactly as you expect it to be, but again, you have to know the lingo to be able to understand it. Um, Examples of these would be wells or hydrants as points, rivers, roads, and pipelines as lines, and watersheds, parcels, and lakes as polygons. I had to dance to that. I could not. What is remote sensing? Right. This is what we've all been waiting for. Now, I've been bringing you guys along, saying we're going into remote sensing. Now we're doing it. So, the science of obtaining information about Earth's surface without direct contact by detecting and analyzing energy that is emitted, reflected, or returned. So, emitted, reflected, and returned are the big parts of that. Obviously, we're dealing with energy too. It's electromagnetic energy. This would take, in order to explain it at a full level, it takes a lot of physics and wave physics, particle physics. It's all involved. So, electromagnetic, that energy that is emitted, reflected, or returned. Now, this brings us to the two types of remote sensing. We have passive sensing and we have active sensing. This is the meat of the presentation now. Passive sensing measures naturally emitted or reflected signals, while active sensing emits signals and measures the response. The big difference is naturally emitted versus artificially emitted from the sensors. So, um, the benefits of passive sensing are that it uses natural energy, which is great. You don't have to provide energy for the system. You do have to provide energy for the sensor itself, but it provides for large scale, long term monitoring. Many data sets are free and publicly available, and it's cost effective for global coverage, allowing for everyone to access the data necessarily. It works in day or night, or sorry, excuse me. Active sensing, however, has many benefits as well, not necessarily the same benefits, but we're going to go into it. Active sensing works day or night in all weather. It has high resolution and it precisely maps 3D under certain characteristics. It can penetrate canopy cover, soil, or water. And it finally enables real time or near real time analysis. There are also limitations to both. The limitations of passive sensing are that it is limited by sunlight. Obviously, you don't have any sunlight at night. It has the fact that the atmosphere can block signals when it's passive. And finally, it has lower spatial and temporal resolution, temporal meaning amount of data points through time. Active sensing, however, it has more expensive equipment, has more expensive operations and maintenance schedules. It requires more power and expertise, and it usually covers smaller areas per scan, leading to higher costs in the end as well. At the end of the day, it's generally a contracted form of data. You're not going to be out there collecting this on your own. You're not going to be out there in the field necessarily by yourself collecting it either. You're going to have a contractor probably with you, or you're going to be an expert. So let me just, oh, that worked. So there are multiple forms of measurement in remote sensing. They both go for both passive and for active sensing in most cases. To start, we have terrestrial or ground-based systems. Most of us are familiar with GPS, GNSS. It is field sensors. You are on the ground, you are taking data from a sensor that you are physically touching. It is high precision, real time, and generally direct validation with minimal processing, especially in this day and age. It is probably the most accessible form of remote sensing. Obviously, most of us are familiar with terrestrial based sensing with GPS and GNSS. The only con is you have obviously limited spatial coverage, it takes longer, and it has higher maintenance. So um, all those factors combined, it's a great resource, and you'll find that within each of these, they're all great to to correspond and bring together rather than keeping them isolated. Which is the general objective: is build layers, don't necessarily keep things isolated. This brings us to airborne, aka drones and aircraft. We have UAV, which I really wish I could remember. It's unmanned aerial vehicle, right? Yes. Um, Imagery, aerial lidar, multispectral cameras. You're putting them all on an airplane or a drone. You're flying around in a grid-based pattern or in a single line, and you're trying to measure the characteristics of the surface below you or the atmosphere below you. It's flexible, it's medium and high to high resolution, and it's very task specific. We have general surveys flown probably every day throughout the world, if not the nation, for surveying, and it's a matter of whether or not it's publicly available, obviously. But they fly every day. They do these surveys every day. It's phenomenal. Obviously, the cost, you have to fly an airplane, you have to fly a drone. Those are expensive. Fuel is expensive. It's expensive to take off at an airport. Everything costs money. The regulations, and it's also very weather dependent. Um, Obviously, with flying and with weather, you're going to have problems. You just have to keep aware. This finally brings us to the satellite. Woohoo! It is the orbital mechanic of remote sensing. Obviously, satellites are kind of the loftiest part of this. Everyone here is like rocket science. It's too far beyond me, but satellite data is available now. It is at our fingertips, and we can use it to augment and implement our services. So this includes Landsat, Sentinel, MODIS, and commercial satellites. You obviously have governmental, commercial, public, private. You have every form of data collection there. The pros are that you have broad and global coverage. You have long-term archives, depending on how long ago the satellite went up. The only problem is generally speaking, satellites have lower resolution depending on the sensor itself. The high resolution satellites, I think, are top secret. So um, it has atmospheric interference at times, and sometimes costly for high resolution data. Can anyone let me know what time it is? 10:10. Okay, 25 minutes in, I think. So that's all those forms, the three forms of measurement for remote sensing. I do think that this is an excellent picture to take. It reminds you the three forms alongside passive and remote sensing, which all of those factors combined should allow you to have a tool set that takes you into the future. Passive sensing cheat sheet. Don't take a picture yet. I go over application as well, and it'll be at the end, and I'll leave it up for you guys to take a picture. So we first have optical remote sensing. It captures sunlight reflected from Earth's surface in multiple wavelengths. Um, it, so the example sensors, those are more just for your reference. I know it's just names at this point. So when you take your picture, those are the sensors that you're looking for, especially for passive sensing. So then we have thermal infrared sensing. I think we're all familiar with infrared sensing when you take a picture and it maps the heat signature. So um, we then have microwave radiometry, which detects naturally emitted microwave energy from Earth's surface. It's not necessarily the most intuitive, but we'll get into it in a second. Solar radiation and albedo measurements measure the amount of sunlight reflected by Earth's surface. And atmospheric sensing analyzes how sunlight is absorbed and scattered by gases in the atmosphere. So we first started by going over general application of all of these principles. For optical remote sensing, we have land use classification. You take an image, you plug it into an algorithm, it starts to classify each individual pixel based on what the signal is saying what we're trying to determine from our data. We also, for thermal infrared imagery, imagery, we have drought monitoring, which I think makes sense. You're measuring heat, it directly relates to drought. Microwave radiometry helps you monitor precipitation, and atmospheric sensing helps you analyze cloud cover and track atmospheric gas. This then brings us to the application that we're all probably more familiar with, water and wastewater. The optical remote sensing is good for water quality monitoring and drought assessment. Thermal infrared sensing is good for water temperature mapping. Microwave radiometry is good for sea ice tracking, and solar and radiation, aka albedo measurements, are good for glacier monitoring, which isn't necessarily useful for everyone. It's more of a Colorado thing, I think, because we have glaciers there too. There's also the urban application of these principles. Thermal infrared, obviously, urban heat island studies. It's kind of hard to read. Um, and solar radiation and albedo, they're useful for climate studies and for air quality monitoring. Finally, we have agriculture application. We have soil moisture detection with microwave radiometry and agricultural monitoring for um, albedo measurements. This is the picture to take. All right, I'm going to move on. I see people taking pictures. Due to Zoom. All right, active sensing cheat sheet. I made this one so you can take a picture right off the bat because I know you guys were antsy for it last time. So this one, obviously, a lot more information, way more processes involved just because it's active sensing versus passive sensing. But we have, I think this is a pertinent question. Who here is familiar with LiDAR specifically? Raise your hand. And so a good majority of everyone. It is light detection and ranging. I think it is probably the most useful application of active sensing, if not the most ubiquitous, because it emits laser pulses and measures the return time to calculate elevation or structural features. So obviously you're not able to look inside of the substance, but you get that air surface interface perfectly, and you're able to figure out, like, I could map this entire room just with LiDAR and a sensor right in the middle that scans the entire room, and create a 3D visual of the room. So the applications are topographic mapping, forestry management, infrastructure monitoring, and bathymetry, which is mapping the ocean or any subsurface below water, if that makes sense. We then have radar, which is radio detection and ranging. It sends radio waves and measures reflected signals to detect objects or surface properties. I think we're all familiar with radio waves. It's how we hear the radio. It's that same frequency band in the electromagnetic spectrum, but you're using it for detection and ranging specifically. So this can be used for land deformation analysis, precipitation monitoring as well, soil moisture detection, and ice sheet tracking. All very lofty. I think again, active sensing is really the hard part of all of this. We also have sonar. I think most people here are familiar with sonar because we all either love fishing or we've all been on a boat at some point. So it uses sound waves to measure underwater features by analyzing the echoes. I think this is a good part to focus on because echoes really are an easy thing to remember. Every form of active sensing essentially emits a pulse and waits for an echo. Just like when you yell, you're yelling and you're waiting to hear the echo back. It's the same principle. You're just measuring how long it takes to get back specifically. Just like when you yell, you're like, hey, or someone yells at you, you can generally, well, I guess you can't tell how far away they are. That's not a good act or not a good analogy. I try to come up with stuff on the spot. This brings us to ground penetrating radar, another form of radar. It emits electromagnetic waves, specifically radar waves, into the ground and records reflections from subsurface materials. This is the most explicit form of geophysics from this survey, from this presentation. Obviously, subsurface mechanics alongside subsurface features like pipeline or like any valve or anything under the subsurface within 10 feet. You're able to map them and create a really good structural overview of your system. This is GPR. If you have the money to survey, It is one of the most useful services that you can possibly apply on your system, in my opinion, uh, at least at the beginning. We then have laser altimetry. It's a form of LiDAR, but it's more single scans. It uses laser pulses to measure land elevation and icy changes. Um, we also have scatterometry, which uses microwave signals to determine surface roughness and wind speeds. Very useful, more for the meteorologist than anyone else. And then finally, fluorosensing, which is an application we're actually all familiar with. You know, when you measure the um, the composition of your water, you're doing those kind of studies, you're doing fluorosensing most of the time. You're measuring the response, the spectral signature of the water and what chemicals are inside of it just based on that alone. So this brings us again to another classification of where we're at. We have publicly available versus privatized data. Publicly available is obviously free. Uh, it's generally put out by governmental agencies throughout the planet. Um, NOAA, USGS, USDA, EPA, they all have their data sets. It generally provides for broad coverage. Of course, this isn't necessarily applicable on the individual scale, but you're able to get more regional observations done with this type of data. Exactly, that it's useful for system-wide planning rather than an individual case study. It may lack local resolution. It may be too coarse for, let's you, parcel scale. It may be containing complex data formats requiring GIS and remote sensing. And it also is limited in its timeliness. It updates are relatively infrequent depending on the satellite or the data source, and oftentimes lag behind real world events. We then go on to privatize. This is the data that you have to pay for. It is tailored to local systems needs most of the time, whether or not that's meters, SCADA, and UAV imagery. It is high resolution and oftentimes real-time inputs. And it also enables targeted decision making specifically, which is obviously the power of privatizing and contracting your own services. It's your data. You choose what to do with it, unless you're purchasing it from someone, in which case they own the data and you choose what to do with it still. Neither here or there. Um, the problems with privatized data is there is a high cost of equipment, sensors, and staff training. Data integration also presents a large challenge. There are oftentimes legacy systems and siloed records, which make it hard to access your old data and implement it into your new data. And then finally, concerns around data ownership, privacy, and cybersecurity are paramount. Um, Obviously, a lot of times people want to, you don't want all of your information being out there, and oftentimes remote sensing does not stop. You have to either pre-process or post-process the data to get rid of signals that you don't necessarily want to see. So that is a big problem as well. We got a picture of that, right? We're all good. I think this is another really important part of it is you want to recognize where your data is coming from, whether or not you have to pay for it, and what you're doing with it ultimately. So this brings us to asset mapping. You'll see my little animation there that cuts around. With infrastructure inventories, digital maps of distribution systems, stormwater networks, treatment plants, and pumping stations centralize asset information. It enables real-time tracking of asset age, condition, and maintenance schedules. Obviously, all very important in our industry. Then we have the concept of digital twins. Is anyone familiar with the concept of digital twins? Raise your hand. Yeah, not too many people. Well, digital twins combine GIS, sensor data, and predictive analytics to create a virtual model of water infrastructure. You essentially you have your data flowing through your pipelines, you have your model representing the 3D structure, and then finally all of it comes together for an individual model that augments your system. It enables real-time asset tracking, leak detection, and resource management, ultimately saving you money and improving operations and making your people happier. Um, we also go over asset structural health, which I went over briefly earlier with GPR, but thermal imaging, LiDAR, and synthetic aperture radar help detect leaks and underground pipe failures. GIS-based hydraulic modeling specifically optimizes network efficiency and water loss. LiDAR and ground penetrating radar also track movement and structural shifts in critical infrastructure. Obviously, LiDAR does what's above the surface, what does what's visible, and GPR obviously does what's below the surface, what's invisible to your eye, but visible to the sensor. On the right, you see specifically we have a thermal infrared image right here, and then this is a GPR scan over a highway, just showing that GPR, it's come so far since I was in college. You're able to drive them behind cars now. You're able to put them on carts. You're able to walk them. It's been revolutionized even since I graduated college, which is incredible. Bridges, reservoirs, dams, and treatment facilities all benefit from temporal analysis of structural characteristics. I think we're all familiar with that. Now, this is, I think, the main part that we're going to look at first is obviously this U.S. drought monitor for 2024. I compiled this image using, I think it was something like 100 images. And obviously, it shows that drought is constantly changing. The way we measure drought um, is always stable, but the measurements do change, obviously. But so we determined this map on the right from generally satellite-based vegetation indices and soil moisture monitoring alongside weather patterns. There are a number of characteristics that go into this map, but we've gone over the normalized difference vegetation index. There's also an enhanced vegetation index, which assesses plant health and stress levels related to water for vegetation. It helps identify drought-prone regions by detecting anomalies in vegetation cover. This is we'll speak into it later, but I apply this, and it's one of the most easily applicable forms of data. All you have to do is plug it into your Esri suite. You plug it into an individual tool, and it'll output it just if you have the right data set. We then have soil moisture monitoring, which is passive microwave remote sensing, detecting moisture. We know that, so we're just going to skip through that. Flood risk mapping using GIS. Hydrological flood prediction is a very useful tool. Um, GIS-based flood models simulate river flow and floodplain inundation using elevation and terrain analysis. I think a lot of us are either flood prone or drought prone, and sometimes both. I think most of us know if we're flood prone or drought prone. So obviously, this is more just get your hydrologic models done for your region, get them done for your system. You know, get as much data as you possibly can as soon as you can is what I say. Um, we have FEMA's National Flood Hazard Layer. That is an easy resource to apply if you're ever curious about it. It's like, hey, I don't know exactly where my floodplain lies. Check FEMA's National Hazard Layer. Um, we then also have, again, synthetic aperture radar. It penetrates clouds and collects flood extent data, even in severe weather conditions, allowing for disaster management and disaster response, and effective disaster response at that. The Sentinel-1 synthetic aperture radar images helped monitor the 2019 Midwest floods. I'm pretty sure it's applied more often than that. Even with any flood nowadays, there's a flood, you can guarantee someone's looking at that data. The image is this is a general weather model that I found on the internet, and I just wanted to show how variable weather is. These are individual days across individual months. So it's not a composite between the months, but it just shows weather changes a lot. We have very variable systems, and it's hard to predict what's even going to happen tomorrow sometimes, you know, so. This brings us to my green space project. I had time.
You got another 15.
15, sweet. All right, well, we're gonna go nice and slow through the green space project. I'm joking. We're gonna have time for questions, and this is gonna go exactly how I planned. So obviously, I have a Gantt chart. It shows where I've been over the last year and a half in terms of developing this project. A lot of my time spent on it is personal time. I love working with people. I love working with real case studies, and that's what this is for, is to determine how to respond to vegetation and green space analytics. We'll go over each individual part as well. But you can see it's been since October 2023 up till now. I've been working on it 2 years now, so. Project motivations, water scarcity and conservation, rising drought risks demand, smart irrigation management. Data-driven decision making is, I'm sorry, municipalities lack high-resolution irrigation insights. NDVI, LiDAR, and machine learning enable precise land use analysis due to advancements in remote sensing and publicly available, the being made publicly available. Climate resiliency and sustainability. It supports long-term water security through predictive modeling. And finally, I would like to have a statewide and scalable impact by standardizing irrigation assessment for applications across Colorado. Project goals. I'm just going to start by showing you guys the map first because I like this map a lot. This is Crate, Colorado, right over here. It was the preliminary process where I just was familiarizing myself with how to map NDVI, how to discretize it into individual parcels, and overall very useful. Obviously, it led me here. So, a pivotal part of the process, while it doesn't seem all that influential yet, it's a great part. So, um, I think I'm going to skip the points because we went over them already. So we're just going to look at maps, and I'm going to tell the story. Um, this is Wiggins, Colorado. That is their NDVI map. You'll notice this time it's mapped per parcel. That was the biggest part of this process, was getting it discretized into every individual parcel, aka parcelized or parcellated. Um, we have NDVI in each individual parcel, and some of them are empty, but it was, again, a pivotal part of the project. Finally, well, not finally, the next iteration of the project, I worked with Vail, Colorado. This time we got the NDVI split into parcels, and we also created a canopy height model, which when you're mapping vegetation, the canopy also makes a big difference. You can't just measure ground cover, and it's a really good idea to differentiate between ground cover vegetation and canopy cover vegetation. On the right, you'll see all of Denver. This one doesn't have a canopy height model, but I parcellated all of Denver. It took me multiple days just to process the data on processing alone. Not supervised. It was just specifically me leaving my computer for 2 days, and then it came out with this. So um, we each individual parcel has an average NDVI value on it. It maps all of Denver, and it just shows the general regional trends of vegetation in Denver. Really cool looking map. Zooming in on that map is incredible. And then finally, we have the most recent iteration where I'm working with Pueblo West, and I integrated every form of data into each other to the point where the map shows vegetation, canopy structure, canopy health, building structure, and we also have water infrastructure as well on this image. Um, Highlighted are parcels over 10,000 usage or 10,000 gallons per month in usage for their municipality. Obviously, when you're dealing with this type of information, it's always good to be discretionary, but uh, parcels are a really good way to analyze images if you're trying to understand your municipality. So you either get your parcel data from the county, from your municipality. I found a lot of trouble getting parcel data from municipalities and from counties, but fortunately for this one, is actually really straightforward. And then finally, this shows that I use machine learning to classify the golf course in an internal neighborhood there. Uh, the it doesn't have a color bar for or a legend for each of these because the colors are represented here. It's really small, so it's hard to see. But you have ground cover. Trees are purple. Ground cover is like the green scale. Um, it's I don't know. I'm really happy about this map. So practical advice. Yes, sir.
Where do you normally get the parcel data?
I mean, it really it depends. He asked where do I get the parcel data. It really depends on the county. I've had counties that don't want to give it to me. I've had counties that give it to me in 2 hours. You know, it's a. I think it really differs on the GIS team at an individual county, and that's why it's good to have county level relationships as well. All right, first point. How do you guys apply this in your lives? Start with what's free. Leverage publicly available data sets, aka NOAA drought maps, USGS streamflow, USDA land use, NAIP, USDA. Use these as baselines to understand regional trends before investing locally. It's also a really good idea to get those publicly available data sets just so you can get the wheels turning, you know. Pilot your collectible data. Rather than starting with a large scale operation, you want to make sure that you are starting small. Deploy sensors or deploy a drone in a one pressure zone or one pilot area so that you're not overwhelming yourself. You're not going too far and having to redo all of it. So, and then finally, you want to test integration with SCADA or GIS before scaling across the system. Very important part. It needs to integrate with all of your systems necessarily before. I mean, it's essentially it's like when you have a map, it's only useful if you're integrating into your services. So you want to integrate all of your data into one source, which is oftentimes SCADA and GIS. Invest in skills, not just tools. You want to train your staff in GIS and remote sensing basics to reduce reliance on outside consultants. And then finally, it's a great idea to build partnerships with universities or regional water associations for knowledge transfer. I know at my university, they love working with water systems. I think it's actually surprisingly easy to approach a school with a unique problem and have them necessarily be interested in throwing a solution at it, you know, not necessarily solving it, but that's what I found. Finally, not necessarily finally, but next, plan for integration. You want to design data collection with future integration in mind, aka SCADA, billing, GIS layers, standardize formats early to avoid siloed data. That should be bolded. Standardize your formats. Make sure it's all in it's again, make sure you can integrate it, and standardizing formats is one of the best ways to do that. Balance your costs and balance your value. That is probably the most important part at the end of the day. Public data is low cost but broad trends. Collectible data is higher cost but high resolution. Use both. Use both of them. Use them both strategically to inform rate studies, asset planning, resilience strategies, and everything in between. That's then that. Everyone, I think no one's taking a picture. Good. This is it. Be the grassroots effort. I I I'm not sure if anyone else is presenting on remote sensing next year, but I'll probably be back presenting on it again, hopefully. And within that, I want to make sure that you guys understand that it's not, no one's going to tell you to do this. Nobody's going to tell you that it has to be done. It's something that you have to choose to help to augment your system, you know? So be the grassroots effort. I think that's why we're all here, is because we all know the power of grassroots effort. So, how much time do I have?
10 minutes for questions.
Perfect. 10 minutes for questions. And I have topics as well.